The topic of my PhD is the hominid biomechanics, so let's get started. The main aim is to track the evolution of the bipedal movement we do when we walk. The main goal is to know, to maybe let's track this in an objective way. When we say that the hominids walk it like we do nowadays, well, it's not so clear, mechanically talking. So the objective is to track with some parameters if mechanically talking they walk it like we do nowadays. So, in addition, there is some mysteries in human walking. So, for example, these are very old data from the 20s. We can see here the oxygen consumption in human walking in downhill and uphill walking, and we can see how there is a minimum spending of energy at inclination of 10% and minus 10% degrees. So this is a very old data, but there is nowadays almost no explanation on why this happens and why it's at minus 10 or minus 12 or minus 14. There's no explanation about that. So this is a goal to explain. So I started with this, and I did a simple physical and mechanical model. And this model I just take into account the potential energy, the variation of potential energy when we walk. So this is a very simple model, but surprisingly, it reproduces the results. We can see how in this graphic the minimum of energy spending is at minus 10% too. So it's good enough to explain that behavior. Sure, it cannot explain at this moment the whole energetic cost, because the whole cost have many components like the basal cost or the kinetic energy or the potential energy, but the behavior of the slopes and the minimum energy spending is explained. So this is due to the potential energy. So the main this first approximation says that the main component of this phenomena is the potential energy. So, in addition, with this model, 1 degree of freedom parameter rises, and this is a very useful parameter because this parameter changes the position of the minimum. So, and this is very important because new data say that the minimum was not just a point at minus 10%, but was a range. So there's not just a point, and this is very important because this parameter depends on each person, depends on the step length and your leg length. So everyone has a K parameter, that degree of freedom parameter, and everyone can adapt its walking to improve and make more optimal the energy consumption when we walk. So this is if you can plot the energy consumption with the gradient and that parameter has a constraint, and that parameter is about from K equal to 1 and K equal to 1.5 for human, because we cannot do steps like 3-meter steps. So there's a physical constraint about this parameter. So if we continue, this parameter, I calculated it with taking some measures in people, in humans. So this parameter has a value for, as I said, from 1 to 1.4 with slightly changes between sexes, but it's surprising that, for example, for Australopithecus afarensis, if you calculate this parameter, you find a parameter of 1.7 with some variations, but we can say that mechanically this walking that this hominid did mechanically is different. So we can maintain the balance better nowadays. So from the walking to the walking we have nowadays, we have improved a little bit with that. So the main goal is to maybe explain if, for example, these tracks in an edge in a very high gradient, if the hominid that did them had walking like we do nowadays, or had walking like the previous stage hominid. So thank you everybody.